In the heart of the design lab, engineers begin by conceptualizing each bone's anatomy, using advanced 3D modeling to ensure every detail mirrors human physiology before moving to physical prototypes. By incorporating precise anatomical references from medical scans and replicas, the team refines bone designs to achieve unparalleled accuracy in structure and proportion. Scaling each bone to fit a standardized human skeleton ensures perfect proportionality, with digital tools allowing real-time adjustments before finalizing designs. Planning for joint compatibility involves virtual simulations to guarantee seamless articulation between bones, setting the foundation for functional skeleton assembly. With blueprints finalized and approved, the anatomical planning phase wraps up, sending precise designs forward to guide material selection and production. Raw plastic resin arrives in bulk shipments, carefully inspected and scanned to ensure it meets the exact standards required for durable bone molding. Each batch undergoes rigorous testing for quality, verifying properties like melt flow to guarantee the resin will form strong, accurate bone structures. Approved resin is transferred into massive silos, stored ready for on-demand feeding into the molding process downstream. Essential additives like colorants are procured and precisely measured, preparing them for integration with the base resin to enhance bone durability and appearance. Final batches are compiled by blending resin with additives, creating the perfect compound ready for mold creation and bone production. Mold design begins with uploading bone blueprints into CAD systems, where engineers craft precise cavities to shape each skeletal component. Tool paths are meticulously programmed for CNC machines, ensuring the molds will capture every anatomical detail of the bones. CNC mills carve out the basic mold structures from solid aluminum, laying the groundwork for precise bone replication. Precision engraving adds intricate details to the mold cavities, capturing the natural textures of human bones for authentic models. Final testing confirms mold accuracy, approving them for the casting process where bones will take shape. Blended materials are fed into injection machines, heated and prepared to fill the molds with molten plastic for bone formation. Molds are securely clamped, and the injection cycle begins, forcing molten plastic into cavities to create precise bone shapes. Under high pressure, the molten material fills every detail of the mold, solidifying the anatomical accuracy of each bone. Pressure is maintained to prevent defects, while initial cooling begins, preparing the bones for safe ejection from the molds. Once set, the bones are ejected from the molds, ready to advance to cooling and further refinement in the production line. Ejected bones enter controlled cooling chambers, where air and water systems gradually reduce heat to prevent warping. Immersion in water baths ensures uniform cooling, stabilizing the bone structures for the upcoming demolding process. Air drying eliminates moisture, removing any remaining heat to prepare the bones for clean separation from any attached runners. Automated tools demold by removing excess runners, freeing the bones for the next stages of finishing. A final inspection after demolding confirms quality, sending the bones forward to trimming and sanding for refinement. Bones arrive at trimming stations, where automated tools remove any remaining flash from the molding process. Precision trimming refines the edges, ensuring each bone's contours are sharp and true to anatomical form. Coarse sanding begins the surface refinement, removing imperfections to prepare for a realistic bone texture. Fine sanding adds the authentic texture, replicating the subtle details of real human bones. After final inspection, sanded bones are cleared for coloring, ensuring they're ready for the next layer of realism. A primer coat is applied first, creating a smooth base that enhances adhesion for the upcoming color layers. Base colors are robotically applied, giving the bones their foundational ivory tone true to human anatomy. Intricate details like veins and anatomical markings are hand-painted, bringing educational value to each bone. A protective sealant is added, safeguarding the colors and details while maintaining a natural bone appearance. After final checks, detailed bones proceed to joint fabrication, ready to be connected into full skeletons. Joint mechanisms start with molding reinforced components designed for smooth articulation in the skeleton. Assembled joints are tested for durability and range of motion, ensuring they mimic real human flexibility. Joint batches are prepared and sorted, ready to integrate with bones in the skeleton assembly process. Bones are sorted and positioned on jigs, beginning the meticulous process of building complete skeletons. Limbs are assembled by fitting joints between bones, allowing for realistic posing and educational demonstration. The torso takes shape as the spine and ribs are constructed, providing the core structure for the entire skeleton. Skulls and extremities are attached, completing the skeletal framework with full anatomical integrity. A final pose and balance check ensures the skeleton stands correctly, ready for mounting on its base. Stand bases are fabricated from sturdy steel, designed to support the skeleton securely for display. Support rods are welded onto bases, incorporating adjustments for perfect skeleton alignment. Skeletons are mounted onto stands, ensuring they remain posed and stable for educational use. Quality control starts with visual inspections, verifying the appearance and detailing of each mounted skeleton. Joints are rigorously tested for functionality, confirming they articulate as intended without failure. Durability evaluations simulate real-world handling, ensuring the skeletons withstand educational environments. Upon passing all tests, skeletons receive certification, guaranteeing quality before heading to packaging. Skeletons are carefully wrapped in protective materials, safeguarding them during transit. Packaged into sturdy boxes and labeled, the skeletons are prepared for efficient distribution. At the logistics dock, packaged skeletons are loaded and dispatched en route to global markets. Upon arrival at distribution centers, skeletons are unpacked and made available, reaching educators and medical professionals worldwide. Looking ahead, innovations like smart sensors and eco-friendly materials promise to revolutionize skeleton models, advancing medical education further.